Good afternoon, everybody. My name is Jens Biegert. I'm with IGFO in Barcelona, and it's my pleasure to welcome you to the first series of the Laserlab Europe Talks, which is an online event which will occur twice a month on Wednesdays at 4 p.m. Central European times on the Zoom platform. We are experiencing, as you know, a unique pandemic, which makes networking difficult. However, I think, at least personally, there are many online events, and so we're probably overloaded with some of them. Nevertheless, we hope that you find the new Laserlab Europe Talk platform useful, simply because we need a platform for networking, for regular information exchange and knowledge sharing. And you might, for example, search for some expertise that exists in the Laserlab network, but you might not exactly which partner can provide something like this. So it's a nice way to exploit complementarities, in my opinion, to also increase the competitiveness, to be able to apply for certain funding calls that will be coming up, and to foster our collaboration. We target a broad audience. That means anybody from PhD students to experts in the field. We might invite some external people if you find this interesting and necessary to cover certain topics, to acquire certain expertise or insight. There is no restriction on any of the topics. So we invite also industrial partner. It can be more applied research, more fundamental research. So we have currently three different events scheduled, and you see them listed here. And you also see already from the format, this is flexible in terms of topics. So with that, I will stop my introduction and wish you a successful event, and again, encourage you to be very active using this tool. Thank you very much. Goodbye.
I will give you a talk about multi-photon 3D lithography of sub-100 nanometers additive manufacturing of inorganics, as was already mentioned. And the work was done by a group of authors within our center, namely Dr. Darius Gailevičius, Diana Gonzalez Hernandez, Simonas Varapninskas, Edvinas Klutas, and in collaboration of Vilnius University, Faculty of Chemistry and Geosciences, Greta Merkininkaitė and Professor Simas Šeklizanovas, as well as Professor Saulius Juodkazis from Swinburne University of Technology. Okay, so, well, so it must work, and it will work. It was tested. Okay, so once again, I will show you how photopolymerization combined with high temperature post-processing can be used for downscaling and, more importantly, converting the material into another substance. Just a question, you are seeing my main screen, right? Not
yes, we see
yes,
your main
screen. Okay, because some strange borders. Anyway, good. So more importantly, to convert into inorganic substances such as glasses, ceramics, and crystalline materials. So using photolithography to make to 3D print inorganics. Okay, brief outline of my talk. So I will introduce, or for the ones who are familiar, remind what is laser mesoscale lithography as a maskless, contactless, scalable, high throughput tool, efficient for 3D printing. Its expansion of possibilities by extending the material choices, widening the spectrum of potentially processable materials towards reaching ceramic and crystalline inorganics, and highlight some specific case example for applications in 3D microoptics, and then summarize everything. So within the talk, I will use, well, definitions as ultrafast laser lithography, which is a main tool for making all what I will show, as a nonlinear light matter interaction known as two-photon polymerization technology, or 2PP or 2PP. There are several acronyms. Sometimes it's called as multi-photon lithography, or just simply laser 3D nanolithography. And currently it's a well-established field of laser direct writing and offers unrivaled precision and as well as flexibility in both rapid prototyping and additive manufacturing. For the ones who are more interested into the responsible mechanisms as well as application, we have a fresh topical review, which basically covers possibilities and comparison to larger scale the 3D printing equipment as well as to highest resolution planar-based UV technology and electron beam technologies. So what we need to know before going into details, so that ultra short pulse lasers are used for 3D printing, right? So if we tightly focus short pulse beam, typically a femtosecond, we can and focus to basically wavelength of its dimension, we can confine the light matter interaction into a small volume proportional to the diffraction limit. And while translating the sample or deflecting the beam, we can point by point 3D structure, just write in the transparent material some predefined geometry by selectively modifying the material. So since it's a threshold light matter interaction, we can have confined volumes, yes, and just by optimizing the parameters, have it strictly three-dimensional. After writing the structure, we put the sample into the developer, so a wet chemistry procedure, and all the unexposed material is washed out. So the liquid developer can be acetone, pentanone, isopropanol, ethanol, or sometimes even water. It depends on the material. And thus, we get revealed a 3D structure, which follows the beam scanned path. And depending on the focusing optics, we can go to diffraction limited dimensions. And by additionally tuning intensity, yes, where average power or pulse energy, the most defining parameter is light intensity, but we can choose the conditions when the both lateral and longitudinal dimensions can be precisely tuned. We need to exceed the polymerization threshold, but not to exceed the optical damage threshold. And within that range, we can safely work within fabrication window, and this additionally allows tuning of feature sizes. Since it's not the topic of today's talk, so I won't go deeper into details what mechanisms can be involved. It can be one photon, it can be 3 photon, typically it's 2 photon or 2 photon process, followed by photoionization, which induces avalanche ionization. But nevertheless, all of these processes can be optimized, whether single ones or in combination work to induce localized chemical reactions, which will result in cross-linking of the material. It means the monomer will be turned into polymer, or more simply saying, from liquid, we make hard details, yes, hard 3D printed objects. So just to sum up briefly, it's a controlled photophysical chemical mechanism which can offer unlimited freedom in 3D nanotechnology. 3-dimensional structures with defined features of hundreds of nanometers, and which can go below the diffraction limit in most of the materials. About 3D printing, yes, if we name it as a technique for 3D printing, so of course everyone is caring what is the resolution, what is the throughput, what or how fast it can go, and it's worth mentioning specifically for that a dedicated portal, yes, 3dprintingspeed.com, created by a group of Professor Martin Biegert from Karlsruhe Institute of Technology, where we simply plotted voxel dimensions and corresponding how many voxels can be 3D printed in millimeter, yes, how many individual volumetric pixels can be made, and in respect to total peak printing rate, as well as in other words, or looking from other side, how much of information can be materialized, whether it's bits, kilobytes, or megabits per second. And as we might see, there are some very precise technologies like e-beam, electron beam lithography, which are pretty slow, or some liquid-based like inkjet printing techniques, which can be very fast, but not very high in resolution. So they are not offering high precision. And of course, there is third dimension, like material. Yes, it depends what materials we can process using one or another tool. And two-photon polymerization, yes, of a technique generalized I'm presenting here today, takes a good place in the sense of both, or covers both resolution and printing speed. And we are very happy to be in top 3 using single beam approach, which enables high flexibility. And just to mention why we need it, is that 3D printing can be distinguished into rapid prototyping or additive manufacturing, and typically rapid prototyping is used in labs for experimenting with novel materials, novel light sources, and so on. Whereas additive manufacturing is a more established, more standardized technique for making some parts, like industrial approach. As 3D printing can fulfill both a CAD/CAM technique, yes, from model to print 3D devices. And we managed to achieve 32,000 voxels per second, meaning that 32,000 individual features can be printed per second. Yes, so at high resolution and high throughput. And why it is important? It is important if we want to fulfill the requirements of both rapid prototyping and additive manufacturing. For instance, such as mass customization, we see 100 structures, which all are different, even though being very, very similar. They all have some features different. They are getting higher in one direction, and in another way, topological charge of this specific elements faceplates is being increased. So the technique is allowing to make many fast and at the same time individual features. Okay, so just to have back to ground or deeper into the lab, the typical setup will consist of short pulsed laser source, whether it would be oscillator or combined with amplifier, which is typically not a necessity for single beam two-photon polymerization, but it can be useful for some purposes. In any case, we'll need power attenuation to precisely control the power, yes, corresponding to intensity at the sample, if needed, and having the possibility light wavelength can be tuned or changed, and the beam can be deflected by galvo scanner or translated on by stages. It also can be combined for some more sophisticated setups in order to make it fast and continuous. And for the ones who are familiar with microscopy, so they will see a microscope here, yes, we have a transmission if illuminated from bottom, or reflection if shined from top. But this allows us real-time monitoring of the 3D printing process, which is very important in case we're working with novel materials, novel laser sources, yes, and we want to see whether we're really doing something before we put into the developer. And scale and material summary or map. So the technique is enabling making features smaller than hundreds of nanometers, while the overall object size can reach more than tens of millimeters, up to centimeters nowadays. And it's a continuous scaling, so it does not have strict limitations. Yes, by changing focusing optics and adjusting laser power, we can have all scales in between. And from material point of view, all kind of organic resins can be processed, whether acrylates, epoxies, vinyls, some biopolymers, and even proteins, which can be cross-linked. More interesting for technology are hybrid materials like doped ones or composites, chemically bounded. It can be glassy plastics or some functional composites. And finally, we approach to inorganics, which are pure inorganics like ceramics, crystals, and so forth. And then from application point of view, so wherever we need three-dimensional complex shape structures, nanophotonics, prototyping, bioscaffolding for cell growth and tissue engineering, and even for material science or some future applications. Thus, I believe I convinced you already that this is a true 3D printing and in multi-scale and also in multicolor. And we'll talk mostly about the red, the most recent, the hot color, and you'll understand why it is hot. So once again, to remind that we have a 3D writing within a resin, a localized photopolymerization, and by following the exposed trace, the 3D objects can be materialized. After developing, they are revealed, and we have a pristine 3D object, which is perfect for making complex shaped objects and for whatever applications. And as one mentioned, but if we add additionally post-processing at high temperatures and use hybrid materials, so we can induce a reaction, yes, or evaporate the organic part and convert it in a crystalline 3D object, still preserving its geometry, and even encounter some isotropic downscaling. Thus, the same technique with additional post-processing can result into metamorphosis of the material, or one could call some alchemistry. Yes, okay, some references where it is described in more details in our recent paper, which is basically featured during this presentation, how to make these crystalline structures. Going backwards and looking at works recently presented by other groups of authors. So pyrolysis was known to be suitable for downscaling structures, and sometimes even combined with, for instance, reactive ion etching. It can be used as a tool for making finer features, really deep, not only deep sub-wavelength, but deep sub-100 nanometers. Yes, so whether alone or in combination, so they can be shrunk and then even made finer, as it was shown in by Gediminas Simuitinas and co-authors. And of course, from application point of view, metamaterials, all kind of optical, mechanical metamaterials, where the properties of such 3D objects are defined not by the material properties itself, but more likely by geometry, by micro or nano architecture. So again, making a 3D template and then applying pyrolysis, they can be downscaled, densified, and provide with ultralight materials. The density is very low, but at the same time ultra strong. Their mass to volume ratio can be exceeded only by diamonds well, as a natural material, even though this one was made from polymer material and then pyrolyzed. So some new material engineering options are opened by combining 3D shaping and post-processing. Getting into more details of what is happening, why it is so. So we look at a two-photon lithography, like super-powered 3D printing for diverse inorganics. And firstly, we polymerize the structure, we write it in, yes, and then we heat it. Heat additionally induce cross-linking, so some further polymerization and densification of a material can occur during this initial heating, or at hundreds of degrees by Celsius. But if we go to higher dimensions, so the organic constituents such as carbon and hydrogen are evaporated, and the inorganic ones are remaining, forming ceramic or glassy substances, depending on the initial material, like silicon, zirconia, or some other prop oxides. And furthermore, by tuning the post-processing, and specifically the initial materials, we can tune the outcoming substance. Yes, it can be turned into cristobalite, silicon dioxide, zirconium, silicon oxides, monoclinal zirconia or tetragonal zirconia, each of them being distinct for the mechanical, optical, chemical, biological properties. So the material, we started with the standard already trademarked as a 2080 provided by Dr. Maria Farsari from Nonlinear Lithography Group in 4th ISL, which is perfect for making whatever, whether micro animals, flexible structures, or integrated microoptical devices, or stacked multi-layer components. It's widely used for microfabrication purposes, and it's very useful for its high mechanical stability as well as low shrinkage. So basically, we get what we enter, yes, by entering the CAD model into the fabrication setup. We highly expect to be exactly or nearly exactly as it was designed, so without specific precompensations. And this I mention by purpose because later you'll see why it is important. Okay, so the geometry and how heat changes it, or does it not heat change? So freeform structures, yes, that's why the 3D printing is famous for, that it can be create arbitrary shaped geometries, but also we're interested in making cubic or volumetric, like filled structures, as well as for whether photonic or fluidic applications, or even mechanics, so periodic porous templates, right? So initially we can make whatever we want, and after heating at 1000 degrees, we get exactly the same shape, just shrunken to 60% of its initial volume. And it works for all the geometries, whether figurine, cube, or a photonic lattice. We just need to let it shrink, so it does not have to be attached somehow, or it will influence. Again, it can be used for the purpose, but if we put it on some flexible legs, or would catch or suspend in within support structure, so the downscaling is isocentric and isotropic, and so it can be obtained as predicted by but converted in dimensions and the material. Some extreme examples of initial structure and after 1000 degrees, so we can see that you can go down to 100 nanometers or slightly below. This initial blurry structure is because we could not gold sputter and heat then, yes, so we just image it without gold sputtering for conductivity needed for SAM, and this one is more clear, but it's the same structure. For going to higher dimensions, just to bigger scale, so we succeeded to make up to 5 millimeters in scale structures, which with tens of nanometers, tens of micrometers in individual features, without any fissure, fracture, or any other kind significant deformation. So it's working for both nanoscales as well as micro up to millimeter dimensions. And the geometry, however we would look from, it looks fine, yes. Yes, a knight targeting to the east as important nowadays, and from all the dimensions and whatever zooming we can have, it shows perfect surface as well as structural quality. Okay, so for the chemical analysis, yes, or material point of view, some scaffolds were made, or they are better for investigation since they have provided larger volume and more of a material to study. So the initial pristine looks like this optical microscope, and if we heat at 1000 degrees, so it shrinks, and at some point it turns kind of darkish, yes, like black or dark gray, perhaps due to attachment of carbon. But if you don't stop and are not afraid of this process and continue heating it, so eventually it again becomes clear, and it was confirmed by both Raman spectra and XRD that there is no carbon left, and so the remaining material is polycrystalline and transparent, which is again important for microoptics and photonics applications. Okay, so this is just the proof that the carbon, which was responsible for polymerizing the structure, eventually can be evaporated, and the downscale structure is purely inorganic. The temperature can be too high, yes, if we go for extended periods and for some specific structures, so we can shrink too much or become lose their fidelity, and even though we see the dancer becomes a sumo dancer, or the template becomes just a cube, but again it can be exploited for some useful applications like for microoptics or so, since the surface smoothness can be increased by simply adjusting the temperatures. About material tuning, so we started with standard trademarked as a 2080, and if we increase silicon amount and decrease zirconium or vice versa, we can influence the outcoming substance as well. So repeating the same laser lithography and heating protocol, by changing the initial chemistry, we can further downscale and achieve even 60 nanometers of individual features, and some more pronounced inorganic crystalline phases. So this was quite novel to apply XRD for small things, and it showed that the higher content of whether zirconium or silicon we have initially, the higher output or like throughput of its conversion we get finally, forming whether more cristobalite or tetragonal zirconia materials, depending on the needed applications. And to determine the resolution or also the geometry quality, so 3D lattice remains the best, or at least one of the best of structures to make, because it covers all the individual feature, the pore size, the filling factor, and similar parameters, as well as overall shape. And so by optimizing the writing parameters, which can reach down to 100 or near about 100 nanometers for raw material, for pristine material, after pyrolysis it's downscaled for 60 nanometers or so, and quite reproducible manner in all the shrinking is symmetric in all dimensions. And as we might see that this is current trending in downscaling, so 100 nanometers in 3 dimensions and out of diverse materials. So during the recent years, we see more and more papers are appearing, and significantly more of them repeatedly are reaching above, or should I say below 100 nanometer scale. And of course, some more, let's say, more targeted applications appear as well. And so, the field is growing, number of publications is growing each year as well, and we foresee it as a kind of a fascinating field in the very nearest future. So talking about future, what's next? Soon we'll have published one of our book chapters in a book regarding ultrafast laser nanostructuring for extreme scales, edited by Jan Bonce and Razvan Stoyan, yes. And here we cover how other materials can be incorporated to additionally functionalize the inorganic matrices, yes, whether silicon can be combined with all the inorganic substances and include carbon or nitrogen or boron or some other metals, which will result in diverse inorganic substances and will benefit from 3D nanostructures. And some properties and technical applications of 3D ceramics could be like heat or thermal characteristics, yes, like thermal shock resistance, thermal expansion, controlled and optimized structures, conductive or insulating structures, as well as for chemistry and medical care. So again, resilient or very biocompatible materials or bioinert ones can be created. Of course, as scientists from Laser Research Center, we are most interested in light and optical applications, so we do care about transparency, fluorescence, some maybe active materials in the future. But for other material engineering options, so it's also useful for making electroconductive, magnetic, and tunable and controllable of these properties in 3 dimensions at nanoscale as well. And the last, as shown here, is mechanical characteristics. So it can be tough, it can be smooth, it can be porous, it can be wear resistant, and so forth. And as promised, now one case example appearing more towards application. So the technique was already established for making microoptics, whether for phase shaping micro devices or integrated optical devices combined with standard platforms like optical fibers and some metal lenses, as well as completely assembled photonic is like small circuits which can be mounted directly on single mode optical fibers, as well as compound lenses which can replace common lenses, but without losing imaging properties and being 1,000 times smaller, and sometimes beneficial by being smaller, as can be 3D printed directly on small chips or integrated where needed. Okay, but up to now they still all wear plastic optics, yes, with inherent limitations of transparency and optical resiliency. And now I will merge what I have just spoken before to what I show here, but applying the same technique and making the 3D structure with a material which we like due to its low shrinkage or no shrinkage, and by intentively introducing some precompensation shape, we can make it shrink to the and get the position where expected, where it's wanted, by putting it on some sacrificial or support structures. And then it's already made an inorganic, like glassy optical component, which can be characterized by its optical performance for both before pristine and sintered material for imaging. And so again, high temperature post-treatment at 1,100 or 1,100 for overnight from laser-made hybrid material. And then we needed to find a proper angle in order that the shrinkage will be recompensated. And in this case, it was something like 70% of reduction to 70%, or by a factor of 1.4, and for lenses of around 50 micrometers. And so how it looks in reality, yes, the lenses on 0 angled legs, on 16, on 26, so 26 or around 27, it seems like to be the most convenient with applied protocol, and resulting into non-deformed micro lens, which then can be put into action. And it was done using Thorlab's USF 1951 target structure, yes, quite standard one for the same comparison reason. And thus the lenses showed good operation before and after calcination, yes. So the only drawback, the field of view gets smaller as the lenses get smaller, but they provide high transparency, high resolving power, as well as good imaging quality. Okay, some numbers, some averages. So it's pretty reproducible process, and focal distance can be repeatedly made as designed. And the isotropic shrinkage also allows assembling of multi-element components. Yes? So not only it's functional, feasible for single element, but also for stacked components. Yes, for basically aligned circuits, optical circuits, and while preserving the transparency and ensuring the high resolving power. There's the versatility of freeform and stacked, both refractive and diffractive microoptics is shown here, as a lens is refractive, but we can mount a diffractive like grating on top of it, and they remain aligned, they remain centered after heating, after pyrolysis, while being converted into inorganic substances. It does not have to be kind of whether centrosymmetric or periodic. It can work also for prism-like structures, as shown here. So it's really kind of not geometry dependent. And some few last slides about the resilience and the functionality of such materials. So, for instance, if you make a polymeric scaffold and put it into ultrasonic bath, yes, and in piranha solution and shake it for 15 minutes or 1 hour, so you see some deterioration and eventually some like more pronounced cracking, fracturing, yes. Whereas for glass ceramic, it shows no obvious deformation or some fractures of appearance, so no cracking. Whether again 15 minutes or 1 hour, and as said, keeping it into a piranha solution. Without going into details about other performed experiments, I would like to summarize the impact of resilience. So it can be thrown into liquid nitrogen, yes, so at least down to minus 200 degrees by Celsius or even lower temperatures, and straightforwardly extracted and let it to dry in the room temperature, meaning in seconds coming back, because the structure is very small, like instantly to room temperatures, being heated to 1000 degrees or above. So even if repeatedly, and as was shown, resilient for both basic and acidic harsh chemical environments, and mechanical yes, impact by ultrasound, and it also shows scalability from high precision features of 60 nanometers to overall dimensions scalable up to millimeters. Once again, it's like the two-photon lithography or optical 3D printing is in nanoscale, is super powered by diverse inorganic choices as of material. And here I come to a summary that by chemically tailoring raw materials and combining with already mature laser direct writing multi-photon lithography, we make an approach which is non-specifically bound into our own equipment, but it can work with other homemade or commercial setups as a material. It can be 3D structured and later on heated and converted into ceramic, and the ceramic or crystalline structures will depend on the heating protocol and, more importantly, on the inorganic ratio of precursors and, of course, the chemical elements themselves. So by ending my talk, I would like to acknowledge Dr. Maria Farsari and Dr. Elmina Kaburaki for providing us with a AZ2080 material from AISBL. Also funding, including Laserlab Europe, as well as our National Research Council of Lithuania, and also Europhotonics program, which allows us for master students to come for half year or 1 year and study, as well as participate in laboratory experiments. And one more note, yes, advertisement of a new optoelectronic advances journal, high impact, open access, almost 10, and welcome to submit your high quality research of optical fields, yes, optical laser related research. And this is end of a chapter, but not of a story. It will be continuous. Once again, summary of some distinguished application, which was also recently published in Photonics journal. Yeah, so it enables material merging. And the final last slide is invitation to continue research and finding the answers together, whether using the Laserlab visits for researchers, which typically is few weeks, but can be very efficient. Europhotonics students coming for 1 or 2 semesters, or even for a full PhD enrollment, which in Vilnius University will occur in June, late June or early July, and we have an open topic on 4D microoptical components. So thank you for your attention, and I give the stage back to Andreas to moderate it. Thank you.